Good day, I'm Dr. T, and welcome to my office. Today I would like to talk about the many hues of iron oxide. As chemists, most of the time when we're working with molecules and various chemicals, they're either clear or colorless liquids, they all kind of look like water, or they're white powders. Kind of dull, frankly. But sometimes we get the privilege of having one that is colorful and shiny, especially if we are dealing with metal salts. Things that, typically will be kind of towards the center of the periodic tables for their cations. And those have the wonderful habit of interacting with visible light, so they get a nice color to it. Now, when atoms interact with light, the way they end up doing this most of the time, now some of them do really interesting things, kind of bizarre quantum physics, but for most of them, the way they're going to end up interacting with light is you're going to have photons of light. Now remember, light is a spectrum, radio waves through gamma rays and beyond on both sides. You've got your spectrum of light, and this is a spectrum because you've got different photons, and photons will have different energies to them. Depending on that energy, depends on where we would place it on the spectrum. Now, in order for a molecule to interact with light, typically the way it does so is that it's going to be taking the energy of the photon and briefly storing it in some fashion. If that photon is in infrared range, typically it's going to store it by vibrating. If it's in the visible range, typically it's going to store that energy by taking the energy from the photon and using that to what we call excite an electron. It's transitioning an electron from its kind of normal packing arrangement, we call the ground state, to one that's a slightly higher energy. Imagine the electron jumping up, and the electron in midair would be that excited state. Now, this doesn't last very long, and the electron eventually transitions back to the ground state and gives off that energy in the process. But that energy does not have to be given off by recreating the original photon. It could be given off in a couple of steps by creating a few lower energy photons, or it could be transitioned not into light energy, but into motion. So we have this photon, it's been absorbed, and it's now not going to be bouncing off and going into my eyes. So now I don't see that particular photon. Any old photon is not going to be able to interact with electrons. They have to be able to actually jump up into an excited state that jump matches the amount of energy from the photon. And so if they have a particularly useful jump, then they can jump there. If they don't, then they ignore the photon. Therefore, certain things will interact with certain photons, and if those photons are, say, part of the visible spectrum, but not all of it, it's going to look like it has a color. Those things that can interact with just about any photon in the visible spectrum are, of course, going to look black. Now, one substance that has a lot of really interesting ways of interacting with photons is iron oxide, or I should say iron oxides, because there's actually quite a few. The simplest conceptually to think of is iron 3 oxide or ferric oxide, or if you're a geologist, hematite. So hematite is going to be a bunch of iron 3 plus cations. This is an iron atom that is short 3 electrons. And it's going to be interacting with oxide ions. These are oxygen atoms that have a surplus of 2 electrons. Now, this is going to be a solid, so they're not just going to be, iron and then an oxygen or a couple oxygens paired off. It's actually going to create a 3-dimensional web, what we call a lattice, of irons interacting with oxides. And you'll have thousands, trillions, quintillions, or more irons. They're really small, so you can have a lot in a tiny little speck, interacting with, once again, ludicrously large numbers of oxides. And these are going to be at a fairly fixed ratio, in this particular case, of 2 irons for every 3 oxygens. But once again, it's not literally 2 irons and 3 oxygens. It's going to be, 2 trillion and 3 trillion, that kind of thing. And once again, a trillion atoms is still a really tiny thing. Now, when it does this, they're not discrete. There are some, motifs or thinking about that as the ions are attracted just by the static charge, which they are, but the electrons don't interact with different atoms. No, the electrons will interact with both an iron and an oxygen, or potentially multiples, but usually it's kind of somewhat focused on 2. Now, when it does this, you have different ways of exciting these electrons, and these different ways can store different amounts of energy. Typically, these are going to store energy from photons. They're a little bit higher up on the energy range for visible light, and thus hematite, aka ferric oxide, aka iron 3 oxide, aka, we got too many names for this thing, don't we, is going to appear red. And it has a fairly meaningful and dark red. In fact, if you've got this and it's artificially produced from the paint store, it'll be called Mars Red, because this is the hematite's what gives Mars its distinctive color. And, well, that was a nice brand name to color it. But we've been using this for quite a while. You'll notice this picture. This is of a bison buffalo-like thing, presumably a buffalo, that was drawn on a cave. This has been used since prehistoric times, and the particular pigment here, or the particular material being used to paint with, is called red ochre. Red ochre is simply finely ground up hematite in clay, obviously depending on the ratio of clay and hematite and the type of clay, because clays are different, and the grind, how finely pulverized the hematite is, you're going to get different types of red ochre. Now, a few things can be done differently. For starters, if you change out the atoms, of course things are going to be different. You'll notice the black lines around that particularly nice-looking beast. Those black lines are predominantly going to be manganese 4 oxide, or MnO2. This Mn, manganese, is right next to iron on the periodic table. So you'd think it would be similar, but slight differences can really dramatically change which photons it absorbs. And in this case, most of them. It works quite well. This actually makes an interesting scenario when it comes to pigments. You've got ochre, sienna, and umber. These are both going to be, or these are all 3 iron oxide-based pigments. Ochre is just the iron, whereas the sienna has a small amount of magnesium 4 oxide, and the umber has a fairly large amount, so it's darker and grayer than the ochre would be. Now, by the name red ochre, it would be implied that there is a not red ochre, and that is definitely the case. There are a couple of different colors. The most famous of the not red ochres is yellow ochre, and this is actually where the word ochre comes from, being derived from the word yellow. So if we look at this picture, we've got some nice yellow pigment. This is from a Roman wall. And in this one, the yellow pigment is yellow ochre. Now, yellow ochre is still iron 3 oxide, but it has been somewhat changed. Within that lattice, so remember the irons and the oxygens are interconnected in this 3-dimensional web that we call a lattice. In this lattice, there is also embedded water molecules. This is what we call a hydrate. It's a compound, but it also has water in it. Yellow ochre can actually be converted into red ochre by heating it sufficiently hot to drive off the water molecules. Now, the water molecules make a slight change in the structure of the lattice, not to mention the electrons from the water molecules are able to interact with the irons as well as the oxides, and therefore creating a slightly different electronic environment. And thus, instead of the red we had for our buffalo, we now have the yellow of the background for this picture. If you are dealing with sienna and umber, of course, if you look in your crayon box, there's always burnt umber. Umber is going to be the hydrated iron oxide as well as manganese 4 oxide, whereas burnt umber, it's been heated, literally burnt, and thus it is no longer yellow and black mixed. It is now red and black mixed, which gives you a darker, redder color. Of course, things can be changed up a bit. Iron is an interesting atom. It and many of the transition metals are what we call polyvalent. They have more than one stable ion that they form. So iron will typically form iron 3+, but it will also form iron 2+. That's an iron that is short by 2 electrons instead of the aforementioned 3. So this is a close-up of some Huesite. Huesite is not a particularly common naturally occurring mineral. Typically you don't see it because the iron 2 tends to be converted into iron 3. Things roam around, want to pick up a couple extra oxygens, and they're like, hey, you could go one less, couldn't you? The Wuesite is going to be a grayish, greenish tint to it. So definitely not red. This one you will see on forging. So once you heat up iron really hot and you forge it, you'll get a Wuesite scale, or on things like iron meteorites, which is a great way to tell, hey, this is probably not from around here, because Wuesite that's on naturally forming rocks usually doesn't end up staying Wuesite for long enough to deal with, but for meteorites, that's a slightly different story. Now, what we do see a little bit more of is this stuff. This is magnetite. Okay, that's a hair clip. And the gold parts of that hair clip are actually gold. This is a technique called Dama Seaming, which is a really cool decorative approach. Forgotten Weapons has a beautiful documentary on this. It's used to decorate all kinds of stuff, including firearms, hence the Forgotten Weapons doing the documentary. So Dama Seaming, you've got gold that's been smooshed onto iron in such a way that it doesn't really come off. But when you have bare iron or bare steel, that will corrode. That will turn into the iron 3 oxide, which you do not want. That's rust. So to do a protective coating, not to mention, boy, that black looks sweet. Then a lot of iron things are treated such that the outer layers turn into magnetite. Magnetite is Fe3O4. In this case, we have both iron 3 pluses and iron 2 pluses in the mix. This gives lots of interesting ways for electrons to do. So this magnetite has a blue-black look. This is what's called bluing, although honestly it looks a lot more black than blue to me. So yeah, slightly different change. We've changed the lattice up. We've got a couple more options for the electrons to buzz around, and now we're able to catch most of the visible spectrum. Not really hitting a little bit of the blues at this point, but we've got a nice blend. And thus you get that kind of bluish black magnetite, which of course in this damascened hair clip is beautiful, absolutely gorgeous. So hopefully that gave you a little bit of an insight into different ways we think about chemicals. Different things can be a little bit different. Iron oxides, different mixtures of iron with different charges and oxygen, and especially if you start throwing in other elements in the mix, there are dozens of different colors you can get with iron. And so it's really an interesting one. So here's just a take on a couple of different colors, a couple of different ways it can be different. With that said, I hope you have a wonderful day, and I will see you next time.